We're here this afternoon at the British Computer Society in London with Professor Quintin Cutts from Glasgow University's Department of Computer Science. Quintin's co-chair of CAS Scotland and has been leading some of the professional development around computing education in Scotland for a number of years now. We're going to be chatting about some of the lessons learnt around computing pedagogy. Quintin, thank you very much for your time this afternoon. It's very good to see you.
Very good to be here.
Is computing taught differently in Scottish schools from how it is in England?
It's had a slightly different history to England. I think back in the 80s, both England and Scotland were teaching what we would think of as some level of computer science. And when England moved more towards an ICT curriculum, Scotland retained computer science in some form. And so we've retained a reasonable body of teachers who would call themselves computing teachers. Although we did dally a fair bit with ICT as well, we do have that foundation. As to whether we teach the same way, I'm not exactly sure how England's doing all of its teaching, and I think as our discussion unfolds, we'll certainly explore some of the ways in which there may be differences.
Okay, thank you. There's a long history of research into undergraduate computer science education. What do you see as the key lessons learned from that for teachers in the school system?
There certainly has been a lot published over the years about why computing is easy or difficult for different students, and I think it's fascinating that research hasn't really got out to schools. There hasn't been a natural conduit. It's not even got between the universities because it's not really part of their... The academic doesn't really get a big bonus by telling their colleagues in a rival university a good way of teaching computer science and why it's difficult. So I think we actually know a lot, and I think we haven't really been putting it out there. And I think the key messages are that computer science has traditionally been taught by computer scientists who know all about it, and their first aspect in life as being a researcher in computer science, and something they need to do in universities is teach, sort of thing. So much of the teaching has not really explored the developmental stages that we should be considering.
We assume too much.
We assume too much, that's correct. We start off from a very high point and teach from there, and I think one of the slides I often use sort of shows the learning steps, and a cloud floats in, because all of us as teachers, I think, often don't realise how much we've learned. It's completely implicit learning. So, I mean, particularly, I think we encourage our students to be building programs far too quickly.
Right.
Yeah, the dominant pedagogy in universities that I think has flowed down into schools is to encourage learners to be actually making programs very early on.
And Pappett's influence of children learn through making things casts a long shadow on practice in school.
Yeah, indeed.
You see this as unhelpful, right?
Well, unhelpful because we use very complex languages to describe what we're doing, and I mean, principally, you and I are having a discussion, we're intelligent people, I can be quite informal and imprecise and ambiguous in my language, and you're going to work it out.
Okay.
And P's superbug, Roy P, the academic, he defined the superbug. The superbug is really where the learner says, why won't that computer do what I told it? And that's exactly a problem of understanding the nature of the programmer and the computer, and treating them as if it was a human to a human, where I write some stuff down, I expect the person I'm writing or speaking to understand what I really wanted, even if it's not quite precise, or at least to ask questions. If they didn't, my computer can't do that. So in computing,
so a model of a programming language and of human language are really should be very different things.
Well, one's a natural language, the human language obviously, and the other is a formal language with a very precise definition. In fact, for any sentence I write in that formal language, there's only one possible meaning.
There has to be. Yes, yes.
Otherwise it wouldn't be a useful computer language. That's right.
Yes.
And a computer therefore will do exactly what I told it. Whereas that's clearly not the understanding. So that's a major piece to get in place.
Yes.
And all around that is the skills of working with formal languages.
So an understanding of programming and programming in particular languages is central to any genuine understanding of computer science, you'll say.
Well, a simple way of putting it is, let's make sure we have reading and comprehension skills in there before we get students to go ahead and actually make things.
Okay.
And reading and comprehension have multiple facets.
Right.
So one facet is this ability to realise that this is a formal language with a definition behind it. The other piece is to make sure that as well as being able to read the language and break it up into pieces, to parse it, to actually see the structure there in the language, to know what each piece means.
Yes.
So to have an underlying model, and so that's a whole line of work developed by Ben Duboulay, or started off. He defined the idea of a notional machine,
Yes.
Which is the sort of minimal understanding necessary to get what this language is actually trying to do. It's like, I don't need to understand
To be able to
bits
read
and bytes.
code, you need to have a mental model of what a computer will do.
To be able to read English, I need to be able to understand what the concepts are underneath the English.
Yes.
So it's the same idea. I need to understand what underlies this language.
Right.
I don't necessarily need to understand it right down to the registers and the bits and the bytes, but it's got to be sufficient that I have a meaning. It makes sense.
Yes, of course. Okay, let's talk a little more about this idea of reading code, of comprehending code. How is that best taught then? In practical terms, what do you do?
Let me say first what I think often happens, which doesn't get it over well, and then I'll talk a bit about what I think we could be doing. So I think very often what we do as teachers, and I certainly hold myself in this position in years past, and maybe occasionally still, is I'll put up some example code, and we'll see what the output is, and then I'll say, well, it's obvious, isn't it? I.e., the mental model of what this code is doing. I'll do one or two examples, and I'll think that's enough because it's completely obvious to me.
Yes, because you have years of experience.
Well, I think what you find happening is that the students all develop maybe a slightly different mental model. And so when it comes through to the enormous amount of time we spend debugging students' programs with them, we're actually debugging their understanding of what they thought that piece of code was going to do. And so here's a classic example. Just take a while loop, and a while loop has a test at the beginning, and then the code, the body, and according to the particular examples that you give a student, the meaning that they might take of how that while loop works is that as soon as anything changes in the body of the code, which may be 1,000 lines long, as soon as something happens that would instantaneously cause the test to give me back false, as soon as that happens, then I jump out of the loop. Now that's a perfectly valid interpretation given some examples given, where in fact the thing that changes is always at the end.
Of course.
If that were the case.
Yes, you can imagine
think of the standard counted loop.
Yes.
You increment the variable at the end, and then so you drop out there, and you might just say, well, that'll mean I'll drop out wherever it happens. But actually, of course, we know that it's you go through every single step. You can only ever jump out from the top. But so you can see how these misconceptions build up. And think of the ridiculous amount of class time we spend.
And nobody, or few of us perhaps, explicitly teach that idea.
Well, the actual model, so we all share it. Now, I might then learn the model wrong, but at least I've made an attempt to make sure we all have a consistent model. Whereas the other one, I'm essentially leaving it up to the student to come up with a model, and we know they all come up with different models because there's quite a literature of misconceptions, and there's great value in knowing them. Anyway, so that's what I think we do wrong. I don't know if you agree. I hope you'd agree. But
there are occasions when I might have found myself.
I might have done something like that. Yeah. Okay, so well, how shall we be explicit then? So we've been trialling a technique in Scotland, which started off by me thinking about, how could I make sure that the student really did understand this whole thing properly. So I started from tracing, because tracing is one way in which we think we're understanding whether the student knows what's going on.
By tracing, you mean writing down what's in each variable?
What's in each variable? A trace table,
yeah.
So hand execution or tracing, something like that. So I have a table, the variables are there, and as you say, I somehow note the changing variables.
And it is necessary to do this by hand. We can't just run a debugger or some sort of tracing software along that tells us the content of these variables.
Okay, so well, we've done a lot more than tracing.
Yes.
I'll come back to that piece in a minute. So your question is, if I did enough demonstrations with them, demos of how things change, would they learn that way, or is it better to actually get them to do it, like to be the machine, to enact the notional machine, to make all the necessary state changes? Would that be better? I think the research shows it's better to get them to do it,
right,
because just watching doesn't really get it in as deeply. You might want to get them to watch it a bit,
this is possible,
and then do it,
yes,
and then do it. So
I'm just thinking here in the back of my mind about Scratch, where you see the variables on the screen as the program runs through. That's not the same as writing down for as working out for yourself what the program does at each line.
If you think of the worked examples research in any subject, so you start off with fully worked out examples where every step is explained and nothing is left to the students. They don't have to work at all, it's all there. And the traditional learning trajectory with worked examples is you go from those to faded worked examples where some of the steps are taken out and the students have to come up with those steps. So I guess I'm saying, well, let's go right to the other end where it's completely faded and the student has to do all the work to make sure they can step through this thing. But let's just come back to trace tables. So people often think that tracing is a good way of getting students to demonstrate they know what they're doing. Tracing is actually hated by students. I mean, I don't know if you've ever discovered that. They hate doing a formal trace.
I remember not enjoying this when I was learning computing myself.
Well, there could be a number of reasons. My take on it is that tracing was a technique developed by professionals, and simple cognitive load theory says I can't hold all of those variable values in my head and keep them updated while I'm also going through each execution of each different step. So they needed to write them down. But the benefit that a professional had is that they actually know every construct like the back of their hand. They have a really clear understanding of what it's doing. They don't have any difficulty parsing the code into pieces like expressions and statements and blocks and lines and all of that. All of that is straightforward. And so their cognitive load of keeping track of where they are in the program, that doesn't get overwhelmed, and all they need to do is write down the pieces. Think of a poor student who hasn't really got a hang of these constructs, not deeply yet. It's not absolutely automatic to look at it and parse it, and as we do in English,
there's a lot of
still struggling.
Required at that semantics.
A lot of their cognitive capacity is taken up just actually parsing the program. Then they've got to remember where the next step is, and they've got all these things to do. So when we really thought that through, we've ended up with a kind of paper-based format where you simply have the program, and we divide some of those activities into stages. So the first thing you have to do is put a box around every expression. Now, man, what an argument we've had in teachers in Scotland about, well, what is an expression? But I mean, it's a piece of the code that when executed gives me back something. It gives me back a value that I don't have to do something with, store it, print it, whatever. So that's immediately encouraging the students to practice parsing the lines into pieces. Can they actually see what the component parts are? Then we effectively get them to draw a flowchart on the code. The key thing is it's on the code, so you actually draw the arrows between the lines, and if you've got an if statement or something, then you draw the appropriate, if it's true, take this route, if it's false, take this route.
This is sort of reverse engineering the algorithm out of the code.
Putting the control flow on.
Yes,
it's very clearly showing the static control flows, showing the possible paths through the program, which, otherwise, when the student is actually doing the execution, they've got to be thinking, where do I go next? They've got to be thinking, is this an expression? How do I break that up? What I'm saying is, let's do these first. Let's give them practice in doing that. to help them for it to become automatic, but also so that when they go on to the next stage, right, so they've done the expressions, they've put the static control flow on, then they start executing the program, and what they're doing there is pretty much doing what we would think of as hand execution, right? So they're working their way through the program, but what they are additionally doing is they number every arrow as they go through it with a step number. So I did this first, I did this next, I did this next, and every time they update a variable, they just put in brackets which step they did it on. And every time they do a bit of output, they put which step did that happen on. And so you
move from the behaviour of the computer program to the state of the variables.
You've got the state of behaviour is kind of connected together. You're linking up this description with what's actually happening.
Yes, that's really nice.
And okay, so we created this thing, and it's called Tracks, which we referred to jokingly as tracing on steroids. But we can think tracing for CS or all sorts of stuff. But anyway, so we call it Tracks, and then we showed that to our teachers in Scotland. We were training up the lead teachers to go out, a bit like your master teachers, to go out around Scotland and show this to others. And in our enthusiasm, because we were so excited by this thing, we showed them a really complicated program. And they just went, "Oh my God, that's impossible! Students will never be able to handle that." It wasn't really complicated, but
what was the program for?
Well, it was still a very simple program. It was only about 10 lines, but it probably had a while loop with an if statement inside it, and it just made it looked reasonably complicated. And I think teachers were a bit freaked out by it. Anyway, so it's one of my favourite stories. So one of my lead teachers, we then said to them, right, well, the first time you're out with the students, we want with the other teachers, we want you to show them this method because we think it's so valuable. And he kind of went, I don't understand it. I thought that was the most useless thing they provided. And but he thought, well, no, but I trust them. They said we should do this. So he thought, well, I'll try it out with my students first before I tell the teachers about it. And so he picked a class where he had plenty of bandwidth. It didn't really matter if everything went wrong. And he tried it, and a penny dropped as he watched these students going, where should that go to? He actually saw them actually making sure they're understanding, and how does that work, and what's really happening, and then which allows you to get in and address the misconceptions if there's misconceptions of that. That's right. Well, you see, originally that's why we had this as paper and pencil. You could just do it as a homework exercise. Because they do the whole thing. You can look at it really quickly. You can say, right, is the output right? No, it's wrong. Okay, very quickly you can see exactly which step they've messed up on, where the sequence of changes to a variable isn't right, or whatever it might be. So you can very quickly diagnose where their misunderstanding was. And that was really my original goal, was I want a full record of the student's understanding so I can diagnose what's wrong really easily. And only then did it come to me that this was a massive cognitive load issue as well, and I was really helping them out doing tracing as a practice. So what the teachers are now doing is they're introducing the constructs this way to get a consistent mental model of how it works, and then the students can work with it either by working through doing it themselves or whatever. So they can see that whole technique. Very interesting. So that's one thing. That's one kind of code comprehension technique. The other one is we recognise that, as it comes from a bit of work I did 5 or 6 years ago in America with a colleague there, Beth Simon, in San Diego, where we were both obsessed by peer instruction, using clickers and all that. We thought that was a really good method, and we were, peer instruction is... I'm interested by the use of the past tense there. No, still am just as interested. It was just in that context we were using it heavily, and we'd sort of come to peer instruction from the physics side, where it was used very much to root out misconceptions. Where is it you don't understand something, and you identify that because you get the students to talk deeply to try and persuade each other why their view of the world is right. So they have to get to their deepest understanding, and so explaining a complicated physics problem. Well, how am I going to explain this in terms of physics deeply to persuade you that my answer's right, or vice versa? So it was very much used
rhetoric as well as logic.
Well, perhaps, yes. Well, Yeah, but hopefully you go with a logical argument. But I think sometimes the rhetoric probably does win out. But anyway, and in that, as we thought about that, and we used it in a CS0 class, a complete introduction to computational thinking class, we very much emphasised the students talking to each other. What we kind of realised is that it's like a barrier to entry into the discipline if you can't talk about it. If you don't have the language of the discipline, how can I describe this thing in front of me? How can I explain it to you and explain how the different pieces work? So we very much thought of this as a kind of communities of practice thing. It's like I've got to help the students talk about this in order for them to be able to explain what they're trying to do or anything at all. Right. So as well as that tracks thing that is really seeing have they got the right mental model of how programs work. How about just encouraging students to develop the language? Because we might assume, we'll say this is a for loop, this is such and such, this is this. We just assume they get it straight away. But how about giving them a program? So this is one of our exercises we get teachers to do. Just give them a program and say, right, explain every line absolutely precisely. What is it? What does it do? It's a for loop. It's a this. It's a for loop that contains a such and such. It's an assignment, from the variable b to the value of a plus c, and that's an integer.
And you do that as students talking to other students rather than...
They can write it down. Just write it down. They can just write it down. I mean, it could be either... No, I mean, this was generated out of that peer instruction work, where, of course, we're getting them to do the same. But the issue here is they have to have the language of the subject to be considered to be in the community. We're apprenticing them in, because how can you talk to anybody? And so that's
or learn from anybody.
Well, exactly the same thing. I mean, if the guy at the front is going on using this language and I don't really know what he's talking about, or she, we're in a bit of trouble.
So what about pseudocode and flowcharting in the less formal sense? Is that worthwhile teaching that, or worthwhile students going through that process of writing out their ideas or drawing out their ideas?
Absolutely, yeah. I have to say that the work I've been most involved in has been more on this understanding side. When you're getting into that territory, we're thinking about, well, how are we going to actually do the doing? How are we actually going to make programs? What do we have to do to look at the world and the problem space and turn what we see there into a solution to the problem using the tools that we have, and
articulating that in some semi-formal language.
So the idea of top-down refinement is not exactly, I would say, top-down refinement is typically what you're doing when you write pseudocode. You're saying, here's the overarching problem. Let me try and write it in just a small number of steps. And that's a pseudocode, and then perhaps I'll take one of those steps and expand it a bit more, and eventually everything will be expanded down to the program code. Decomposition. What did I call it?
Top-down...
Something like top-down decomposition, whatever. Top-down refinements, and I think that's generally been not exactly discredited, but the thing is, if you use only that as your assistant to helping somebody understand how to program, it's extremely difficult because they haven't seen enough to know the right ways to split the program up into pieces.
So they can't generalise a pattern which they've seen in other circumstances.
That's right. Of course, it's helpful in the sense, well, once they have seen enough patterns that they at least start to decompose in the right kind of ways. It's always useful to plan out your thinking. I mean, you plan out an essay, you plan out your plans for a holiday, whatever.
Don't just sit down at a keyboard and start typing.
Well, as we know, you end up with a whole load of stuff, and you go, but that's completely wrong, isn't it? And then you go throw all of that effort away. Whereas if you thought about it more carefully, you come up with it.
So this is a planning thing.
Yeah, I think so. Where in terms of introducing new pedagogy, I guess where we're coming from there is to say, well, what about making more use of worked examples as a way of, the plumber's apprentice goes and watches the plumber do a lot of plumbing, and they do useful things in the background. They carry out the hard stuff, they hold it when it needs, but they're just looking and learning. And should we be really doing a lot more of that in terms of worked examples where we're getting the expert to articulate why they're doing it the way they're doing it, and then they are seeing the thing being built and the pieces and the
I can imagine that working very, very well. Walking through the process rather than here is my finished program.
And there's this idea of sub-goal labelling where each step of the way you write you have a useful and easily remembered sort of term to go with that stage.
Yes.
Now, quite what those terms are, I don't know if I'm quite sure.
Scaffolding, the construction,
Scaffolding,
the artifact.
Yeah, and it's certainly been shown that you can do worked examples, but if you do worked examples where you're labelling the steps in a useful way,
right.
it's just cognitive load theory. You've got something to attach onto. Oh, it's that step. And that's that step, rather than dun 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 dun. You know, it's helpful to break.
But by labelling it by using language, it's more likely to stick in memory. It seems. Okay. Finally, I think the block-based language, text-based language thing. What are your views on programming in languages like Scratch? A helpful step along the way?
Well, I think the first thing to say about these languages is that they are Turing-complete languages.
Okay.
I mean, you know, they have everything you need to solve any problem in the universe.
Sure about Scratch Junior?
No, I think you're right about Scratch Junior. I think you are right, but Scratch and Alice certainly have everything that you need. So from the point of view of power, they're just fine.
Yes, given enough tape.
Well, yes, indeed. And so what do? They obviously take away the problem of syntax errors.
Yes.
So that in terms of writing code, they simplify things because they take a whole class of error away because you can only put
which
blocks
must
together.
help in terms of cognitive load.
Yes, absolutely. Yeah, absolutely. In terms of code comprehension, they might help a bit because they make more explicit the structure of the code. So it's easier to look at and see the extent of that loop. You know, whereas in Python you've just got to watch out for the indent or a blank line or whatever.
Here we're actually colouring in the indent.
Well, yes, it's so that seems plausible that would help. But in terms of giving you a better underlying model, that notional machine, I don't suppose there's really any great difference. Okay. Well, it depends what one thinks of as the notional machine for Scratch. There's something we're working on right now in terms of my colleague. I kind of wanted to say, when I say we, a lot of this work's been developed with Peter Donaldson, who's a teacher in Crieff High School, but has read loads of research, really more papers than I have, and was my collaborator on our professional development program. But Peter's currently working on a kind of tracks for Scratch and kind of what that would look like.
Right.
What's the minimal that I need to understand about what's going on in Scratch to understand it? And my argument's often been, well, the great thing about Scratch and Alice is that everything is on the screen. There's nothing hidden. That's the kind of notional machine. But there are variables in both these languages that you might use or might not use. There's still kind of hidden behaviour you need to understand. I mean, to actually understand, well, what's happening with that for loop.
Yes.
That's not exactly on the screen.
And especially when you get into the whole multi-threading thing.
Well, what on earth's going on? Yeah, I mean, it's
how many scripts can you have?
It's that kind of hidden. Yes, it's that hidden little thing that it was when we did Haggis, we tried to look at different languages and write the same program, and immediately you realise that just a simple program that acts on two objects, you can't write that in Scratch unless you start using broadcast and all sorts of the comparability between languages is not straightforward. Anyway, I think they're very engaging languages. As I say, they simplify the construction of code, which must be good. They're just as powerful as any other language. But from that point of view, they're just as complicated as any other language potentially as well. So potentially, it's still hard to. I suppose one thing that I often say is, because I use Alice, I often think about this in terms of Alice. When I say the problem is quite close to the solution. So when I say, oh, my problem, I've got to move that cow over there. Cow, move 10. The code is very like the problem. Yeah. And I think that is definitely a simplification. At a level, it's easier to conceptualize what the code means because it's expressed in terms so close to my problem. Whereas, imagine writing a machine code program to solve a particular problem. I mean, it's semantically or cognitively, it's way down below the lower level, and I might have to write.
We kind of want computers to do that sort of thing for us.
Well, yeah, absolutely, yeah, to turn that into that. That's right. But I mean, even Python, or I mean, everybody's teaching Python now is a cool thing to do. Well, but I mean, I don't single out Python.
Do you have a view on that?
No, I encouraged our department to pick up Python in, well, I can't remember, 2005, I mean, a long time ago. I do have a view, interestingly, because at that point I really loved the fact that a simple problem turned into a fairly simple program. There wasn't lots of cruft.
That's nice.
It wasn't like Java, it wasn't like you had to have all this boilerplate for the simplest little program.
Yeah.
And being a computer science person, and in fact my PhD was all around languages, I liked the indentation and the simplicity. And one of my colleagues kind of said, yeah, but for a novice, taking away all of that syntactic scaffolding to the absolute minimum actually makes it harder to understand code.
God.
Now that hasn't stopped us using it in our first year, but
I'm surprised by that view.
But does it make sense? There's no scaffolding. You just talked about the fact that that you coloured it in, and that's a syntactic scaffolding to help you read the program. And so if you think about Python, every single symbol is significant. Whereas you could argue that if you were to use indentation, you'd get rid of curly brackets in C or something. I mean, you could, or in fact, if you look at Alice, they put a whole line scratch. There's lots and lots of words in there to help you understand what's going on. You could slim down those words to nothing, and then you'd be more like Python. But the words help you understand what's going on when you're reading the code. So
Interesting.
Yeah. Who knows what the perfect teaching language is? I don't really know.
Okay, so to conclude, at the risk of trivialising all of this, what are your 3 top tips for computing teachers wanting to improve their pedagogy?
Well, I think it comes out from everything we've been saying.
Yes,
really.
right,
Get your students talking about their code.
Yeah.
Get them talking with each other, with you. Make sure they give them an opportunity to learn the language of the discipline so that they can become members of the discipline.
Yeah.
So I think that's crucial. Plug for peer instruction as being a really good way of doing that. Scottish teachers have really picked that up and found it valuable, so that's good. And the other one is make sure they have a good mental model. Make sure there is a consistent mental model across your classroom of what each one of these constructs means. Yeah. Because then you can have discussions.
Yes.
If you don't have the same understanding, it makes it very, very hard. So that's 2. 3 top tips. Racking his brain. This is relatively unexplored, but I mean, consider worked examples. So in all of this, don't jump to solving problems too quickly.
Interesting.
Or make sure you're doing understanding along the way. One step towards solving problems is to use code examples to let students start to develop the patterns. Yeah. And in any subject, expert problem solving is based around patterns, not about solving from first principles.
That's true. Quintin, thank you ever so much for this.
Really enjoyed it.